Thank you. Hello. I want to start by thanking the organizers, Anna, Derek, Alejandro, Ash, for really the organization of this very nice workshop and conference. So it's really an honor to be here today. And yes, I'm going to use this time to tell you a story about entanglement generation with strong symmetries. So the participants or the main characters of my story are going to be long-lived multi-level atoms that enjoy supercoherence. And for that, what I mean are atoms that typically have two outer electrons. So they are in the second column of the periodic table, like strontium here, or others with similar structure like ytterbium. And these atoms, as I said, has the characteristic atomic structure with outer two valence electrons, which give them a unique structure with a ground state that has a j equal to 0 state. And therefore, this is a singlet state, the ground state. And this state can be coupled with a metastable excited state. And the interesting part is that these electronic states have transitions that are both dipole, j equal to 0 to j equals 0, or spin forbidden, then singlet to triplet, and therefore can be very long-lived. For example, we have the line width of the triple one transition can be of the order of 7.5 kilohertz, time scales of around 22, 21 microseconds, and the triple zero states, for the case, for example, of the bosonic isotope strontium-88 is forbidden, and for the case of strontium-87, that is a fermionic isotope that also have a nuclear spin internal structure with I equal to 9.5, allow some admixture of this transition but still is really narrow, just of the order of a few millihertz. So in fact, these atoms are used as the basics of the state-of-the-art atomic clocks. And what I'm going to tell you here is that they are also exploring a very nice blank background playground for exploration of many body physics. Okay, so in this talk, I want to tell you two stories. First, I'm going to tell you a story about dissipation-induced superradiance. This is an experiment that was recently implemented at JILA. And then I'm going to tell you a story about a follow-up of this experiment that has to do with very phase and strong symmetries. So before I start, I want to start by acknowledging my collaborators and the people that made possible the work that I'm presenting today. This is my theory group. You see a group of very nice graduate students and postdocs that have done a lot of excellent calculations. And particularly, I want to acknowledge Diego Barbarena and Jeremy Young, and a very close and exciting collaboration with the cavity QED group of James Thompson, and this also his group members, in particular Eric Gillon and Dylan Young, who took the data that I'm going to present today. Okay, so I'm talking a story about long-lived dipoles. So, and one of the big advantages is that they offer us to operate in a new regime of cavity QED, where we have an atom that is coupled by light that in the cavity to an electronic excited state that can live long enough that I can use it as a qubit or circuit for my quantum simulation of my quantum or for metrology without the need of just adiabatically eliminating the state. So in this case, what we are going to do is we are going to place the atoms in a single mode. This is a standing wave cavity, and for the purpose of this talk, I'm going to first focus in the case where the cavity mode here talks to the triple one state that is going to be my excited state, and delta C is going to be the tuning between the cavity frequency and the atomic transition. So in this case, I can write a Hamiltonian that describes the coupling of the atoms with the light that has this characteristic, the tuning of the cavity mode. And then we have the standard Tavis-Comin model, where here we are going to have the collective operators J, and then we have the dissipation of the cavity that sets a jump operator proportional to a square root of kappa that is typically of the order of 100 kilohertz. So in this transition, now I'm going to ignore for the moment the clock state. It's going to enter later. And well, we are going to deal with, as I said, with these collective spin operators, and I'm going to call the operators between the ground and the excited state J, these collective spin operators. So we are going to operate in a parameter regime, and that's what we want, very long-lived dipoles, where this decay rate is very small compared to the other parameters in my system, in my Hamiltonian. And we are going to operate in the regime where either the cavity detuning or kappa are larger than n being the number of atoms, the square root of ng, and this g is the single photon Rabi coupling in the Hamiltonian. And in this case, what happens is that the photons only serve as mediators of the interaction between the atoms, and therefore I can adiabatically eliminate them, and this means that the cavity photons are going to always follow the collective spin operator. So there is a one-to-one relation between the two, and in this regime, I'm able to actually replace this field into the Hamiltonian back, and as a result, I get two terms that are important. So the first is actually Hamiltonian, a unitary evolution that is an exchange interactions that means that an atom in the excited state can emit a photon into the cavity, and this photon is absorbed by another atom before it's leaked out of the cavity. And this gives rise to flip-flop interactions everywhere, no matter the distance of the atoms. There are collective exchange interactions that are characterized by a parameter chi here, that I write here. And well, these interactions have been very important in different aspects of quantum simulation, not only in cavities, but in many other systems. So in the case of cavities, we have explored many of the dynamical consequences of these exchange interactions, and in particular, for example, they favor ferromagnetism, they favor spin alignment, and therefore they open a gap between the collective state and the one when have one spin flip, for example, and this has important exciting consequences that James is going to, in the next talk, he's going to talk about. But here, I just wanted to briefly mention that one of the, for example, interesting consequence is that the interplay between these exchange interactions and all their collective drives or system can give rise to some type of dynamical phase transitions or that give rise to drastic changes on the long-time properties of the state of the system. These are unitary evolution, but by changing the system parameters, I'm able to tune the properties of the state of the system characterized by another parameter that has an abrupt change at the critical point. And well, we explored, for example, the consequences of the collective Ising model with transfer field that is called the Lipik-Meshkov-Glick model here. Or, for example, when we go beyond the collective regime and where we add a little bit of type of disorder, for example, we have an inhomogeneous longitudinal field. What happens is that this Hamiltonian nicely reproduces the Hamiltonian that describes BCS superconductors. The story is just that the exchange interactions simulate the attractive interactions between the electrons that give rise to the formation of Cooper pairs, whereas the inhomogeneity from the single particle terms emulate the kinetic energy of the electrons, and the competition between these two is what gives rise to these distinct dynamical phases that we explore also in different experiments. And so I don't have time to talk about this, but I will be here this week or also next week if you have any questions. So, but for this talk, our main feature, or my most important feature, is going to be the dissipation. So in this case, besides the Hamiltonian, we are going to have a net jump operator that is characterized by a rate capital gamma that has this form, and this is responsible for the collective of superradial emission of the system. So for this, it's important to know that the ratio between the chi and gamma is the ratio between the detuning to the cavity kappa, the dissipation, and therefore this can, by changing this ratio, we can tune the interplay between these two terms. And well, here I'm going to set, in the case where this delta C is 0, I'm going to set my atoms and my cavity on resonance, so I don't have any type of elastic interactions. So the dominant part of the dynamics is given by this collective dissipation that is said by this collective jump operator J minus. For the people that prefer cavity parameters, this capital gamma is related to the coevaporativity by C times gamma, this gamma, little gamma gain the spontaneous emission. The idea that atoms can collectively emit when they are all talking to a common cavity mode is a very well-studied phenomena back in the 50s, first proposed by Dicke, and this gives rise to the phenomena of really superradiance in the broad sense. In this talk, I want to introduce a very simple way to see superradiance that is just a rotation, a collective rotation, but it's a non-linear set of rotation, or more or less a self-induced Rabi rotation. And the idea is very simple. What happens is that just classical, you have a rotation of a collective spins, but here, what says the torque of the rotation is going to be proportional to the self-radiated field of the atoms that generates an electric field that is proportional to the dipole moment but perpendicular to it. So you can see that this is actually a nonlinear term that is going to depend on the magnitude of the dipole and is perpendicular to it. So basically, if you have all the atoms in the excited state and there is no dipole moment, of course, but then there is some quantum fluctuations that drive some little dipole moment, then the process starts, and then you started to see the rotation introduced by the superradiant electric field, and then the rotation starts to increase because the rate increases because the length of the dipole starts to increase. It becomes maximum at the equator, and then I didn't continue my movie, but you can see that the difference is that it stops when the atoms are both all in the south pole. So this picture, and this rotation, this superradiant field is going to be very important for this talk. But I just wanted to mention that there are also a very similar way to understand superradiance that is in the Dicke manifold, a set of states that are permutationally symmetric, that is you start, these are the J equal to n half states that, as I said, it's a fully permutational states. And then if you start from the excited state, what happens is that you're going to start to leak down, going down the ladder, having a maximum rate at the equator, and then you go back to down to the ground state. All right. So the idea of superradiance, as I said, has been studied for many years back. But something that is interesting is that in typical dipole-allowed systems happens too fast. And that's why one of the advantages of these long-lived atoms is that it's allowing us to see the transition in real life, in real system, in real time. So, for example, if you look at what is theoretically the intensity that scales like n squared at the peak, and the time that grows that is faster enhanced by the rate is enhanced by n, then you can see that depending on the atom number, you have a delay time and then the peak. And this is theory, but you can see that in a beautiful experiment done by James a few years ago, by using the clock transition, where you see that this gamma is very tiny, is the order of less than millihertz, but he can put 10 to the 6 atoms in his cavity and see actually very nice superradiant bursts with the intensity as you expect and the delay that you expect. So this is very nice. So, well, in this talk, I'm talking about entanglement. So, my wish list when I started to think about these problems is, okay, can we have a system where we have dissipation, but in the steady state becomes entangled? That would be perfect, and that's what we all want. And well, the idea is that the problem, if I have superradiance, then in the steady state is trivial, all goes down. So no way. But what about if I try driving the cavity? So let's imagine that, well, the idea that I would have is that, well, let the system have superradiant emission is an interactions, and therefore it can generate entanglement, but then in order to maintain it or to generate it really, then there is a drive that contrapresses the decay and maintains the block vector at a finite magnetization, not in the south pole. So that's the idea, and that's what I want to explore. Can we do that? And the important part is interesting that this idea is not new either. So this idea of having superradiant emission with collective coherent drive has studied many years back. So this is the Hamiltonian when you have the Tavis coming model and you are now driving the cavity. I do the drive in a specific phase and the dissipation such that this is the Hamiltonian, this is the dissipation, and when I adiabatically eliminate the cavity mode, then I have a Hamiltonian that is just a rotation along the x direction by the drive that I apply, and I have the collective jump operator, J minus. Okay, so this Hamiltonian has been, as I said, studied for many, many years back, and a lot of theoretical investigations, but only recently it has revived again and has caused a lot of theoretical and experimental interest. On the theory side, well, the idea of non-equilibrium phase transitions are really, really nice. Also, the idea of that we can generate entanglement via dissipation, but could be better. There is also the idea that this can allow some type of continuous time crystals, stability, three critical points, and well, this is just a few papers. I'm sorry, I might have missed many of them. On the experimental part, there is a very nice experiment in Antoine Brouillet, where he was trying to see if in free space we can get superradiance, and he saw what he initially thought some type of possibility of having that, and that he thought that was the case, but a better understanding of the system, actually, it concluded that it was not exactly that. So up to last year, there was not experimental realization of this cooperative resonance fluorescence. So does this change? I'm going to explain. So before, I'm going to tell you a little bit of the dynamical phases or non-equilibrium phases that we expect. So in this case, there are two steady states for when you have the pure collective limit, and those characterized by the spin projection in the steady state, JC. And the advantage is this transition is mean field. So I just remove the operators, look at the C numbers, write the equation of motions, and actually look at the steady state. And actually you find, as I said, there are two phases. So there is one phase that we call the superradiant phase. And in this case is when the steady state can be found where the JC is actually finite and below the equator or at the equator at the critical point. So basically, you solve the equations. I mean, there is nothing along the block vector is always zero along the x direction that when you are driving, but the block vector has it has a projection in the y plane, and the balance is between the two, the superradiant drive, the coherent drive, and the superradiant electric field. And between these two, you can see that we can get a balance at this value of theta. And the critical point happens when theta reaches the value pi half. Beyond that, you cannot stabilize a steady state. And this is at the point where you go to the normal phase. In the normal phase, what happens is the drive is so strong that cannot be compensated by the emitted field. And therefore, this block vector starts to rotate. There are finite number of photons in the cavity. This is in contrast to the superradiant case where there are no photons because everything is balanced. And these people sometimes call it the boundary time crystal because there are persistent oscillations in the system, even if with dissipation. So this is the collective case. When we jump and add spontaneous emission, there are a few things that change. Now superradiant decays, in contrast to the prior case where the total length of the block vector is preserved, J square is conserved. When you start to add spontaneous emission, that's no longer the case. We are going to shrink the length of the block vector, and therefore atoms start to radiate a small field. So when the atoms start to radiate a small field, then there is a net electric field generated inside the cavity, and this restores J minus. But because the block vector is smaller, it reduces the magnitude of JC, the absolute value, pushing it closer to the equator. But because spontaneous emission also wants to push it down, what happens is that it changes the order of the transition from second order to first order. So you can see that in the presence of dissipation of spontaneous emission, there is a jump in the order parameter at a value that is of omega of the drive that is smaller than before by a square root of 2, and the transition goes from a first order case. But besides that, well, things are kind of similar. Okay, so the nice part is that we started to explore this phase diagram in the experiment. And the experiment, as I said, it used the 3p1 state. Lifetime is approximately 22 microseconds. This is the setup that the experiment used. So atoms were in the cavity, they are prepared 10 to the 3, 10 to the 4 atoms in the ground state. Then they measure the number of atoms in the system by vacuum Rabi splitting. And then what they do is that adiabatically turn on the drive. After that, they stop the drive at the value that they wanted, and first they wait until the system reaches the steady state, but short time, of about 5 microseconds. Then they do the measurement by shelving the excited atoms to the excited state, measure the number of atoms in the down state, and with that they can extract the order parameter, JC. So these are the measurements of the spin projection. This is after this time, as a function of the strength of the rabbit drive. This is for different atom numbers from 3 to the 3, 10 to the 3 to 2 times 10 to the 4, and you can see the different behavior from a small atom number to large atom number. But the interesting part is that when we actually normalize, not respect to the single particle drive, but respect to the critical point, that was shifted for the expected point by a factor of 0.7 because of inhomogeneities in the cavity couplings. Anyway, we can see that all of the curves collapse. And in fact, you can see that they are aligned with the numerical simulations from theory. These are mean field numerical simulations. These points here are just shadow because when the system starts to have a lot of atoms in the excited state, then the shelving technique doesn't work. But you can see here that you can see here that there is a discontinuity always clear in this plot. But maybe you can tell me, well, but this is not clear if there is a phase transition or not. Well, let's look at the light and see if there is actually a transition. So instead of measuring the atoms, now they look at the transmitted light. They collected the transmitted light, and they try to see what is the transmission as a function of this normalized Rabi frequency. And very nicely, they see not light below the transition in the superradiant phase, and then as soon as the system starts to go above the equator, they see a burst of light, light coming out into the cavity. So I think this shows that we have this phase transition. Now, at longer times, spontaneous emissions start to kick in, and we expect a first order transition. So instead of working into 10 microseconds, they wait for longer times. Same protocol that I showed before, now to measure again the spin projection. And these are different data sets as a function of time, this time. And you can see we classify this time in units of the single particle spontaneous emission lifetime of the system for different Rabi frequencies from weak to strong. And you can see that for the weak, the solid lines are theory, and you can see that for the weak drives, the system remains trapped, like the magnetization remains below the equator. But as you start to increase the drive, they start to trap and then go away, and for others, similar things. So this, as you increase, there is some change in the steady state that is different from the metastable state. And in fact, when you plot the spin projection as a function of the normalized Rabi frequency, we can see that for short times, we see the characteristic second order transition that we saw before, but as we wait for longer and longer times, then this transition is changing, and instead you are going to see a jump in the behavior as the first order transition. So that's nice. So we have seen evidence of this first order transition in the system. Just in the light, again, to make sure that we also see the same effect. In fact, if we look at the light, you can see the same behavior, that is the changes of depending on where the time that you wait. All right, so just last experiments that we did at the beginning, I mentioned the effect of the elastic interactions. So we, in the experiment, what they did is remain the drive and the atoms remain on resonance, but they change the cavity frequency to introduce some net detuning. And in this case, the interesting part is that in the process of detuning, both the rabbit drive inside the cavity and the superradiant fields are normalized by the same amount, and therefore, when you look at the critical point, it washes out. You don't see any difference. And in fact, this is what is here in the experiment when they change the detuning by a factor of 5 kappa significantly, and we don't see any change in the critical point. Okay, so now what about entanglement? So this is a very nice experimental implementation, but we wanted to go beyond that. So in fact, it has been very nice work that have shown that when you are very close to the critical point, the interplay between the drive and the dissipation generate a spin squeezing. You can characterize the spin squeezing that actually scale with the number of atoms, but on the other hand, the problem is that this squeezing only happens very close to the critical point, and then if you turn off the drive, it will disappear, you lose it. So what can we do better? So we have a story that I cannot tell you today that using dark states in multi-level atoms. This is a way to go. But the other story that I want to tell you today is the use of strong symmetries. Okay, I didn't know about strong symmetries before, only when we started working on that, but you have a Hamiltonian system. Well, you know that if you have a symmetry, it's because you find an operator that commutes with the Hamiltonian, and this says that this is a conservation quantity that is conserved. Well, in the case of open systems, it's the same, but it's a little bit more complicated. So you have a master equation like this one with jump operator L. What happens is that now the symmetry can be classified into two different classes. In one class that is called the weak symmetry, what happens is that what commutes is the Liouvillean of the master equation with the super operator of the symmetry operator. So it's the other way to look at that is that it's conserved kind of on average. So a simple example is that if P is the parity operator and you have a jump operator that is A, the loss of photons, what happens you can see respect to the parity. If you have even parity, you can go into if you have odd parity, you can go into even parity. If you have even parity, you can go into odd parity. So you have trajectories in principle when you switch from two different types of symmetry sectors. But on average, you can find regimes where it's conserved, on average. This is different when you have a strong symmetry where the jump operator directly commutes with the symmetry operator. So in this case, therefore, for example, imagine a case when the jump operator is A squared. In this commutes with the parity, and you can see that you always go from even parity to even parity or odd parity to odd parity. So during the trajectories, it's conserved every time. So it's not on average, but every time. So let's try to use this in our system. So what we are going to do now, we go back our clock state. And imagine that we have these three levels, but now I'm going to create a coherent superposition between the ground and excited end, the up state, the clock state. For the strontium 88, nothing happens. There is no way that this can decay here. For the case of the strontium 87, it's going to be very weak. So basically, we can assume that this state is not coupled to the cavity, or there is not dynamics of this clock state. It's frozen, basically. So the idea is that in this case, we have a strong symmetry because the number of particles in the excited ground manifold is going to be conserved. So this is a conserved number, and you can see that any collective operator or any operator in the J sector is going to commute with the number of atoms, and therefore this is a strong symmetry, satisfies the criteria. So this is the protocol that I propose. Let's create a superposition, coherent superposition between the ground and the clock state. So you can see that in this coherent superposition, the number of atoms down is not fixed, but you have a Gaussian distribution with peak at the center and n half. And we have two different block spheres. The block spheres between the down and the excited state, and the block sphere between the up, the down, that is a coherent state, pointing in this case along the x direction. Okay, this is what we do. Now we're going to drive the ground excited transition. Let's drive it. And what we do is then let the system reach the steady state. Now the system is going to, for each nj sector, similar physics that I told you before is going to happen. The system is going to relax to a state along a fixed direction that depends on nj. But on average, if we are looking at an average value, it's going to relax to a coherent state with this average value pointing along a specific direction. We call this state 1, and in the 0-1 state, you can see that we recover a coherent state pointing along the x direction. This happens after the dissipation, after we let the system reach the steady state, and this preservation of coherence is thanks to the strong symmetry. Okay, the next step is that now I wanted to let the system evolve, and the evolution that we do is to add the tuning of the drive respect to the atomic transition. That means is that I'm going to move the drive, add a phase to the drive, so it's going to be rotated along the xy plane. And I'm going to do it adiabatically so that my block vector is going to follow. So this is going to do, I'm going to move the drive, and my block vector is going to do that because it's going to be adiabatic. The question is, this procedure, what translates this procedure in the S block sphere? What do you expect? Okay, so if we look at the mean field Hamiltonian and we try to solve the equations where the G minus in this E down manifold and JC, we are going to solve the equation of motions in the presence of the detuning. We can see that in the steady state, both the D and the E operators, the down, D is for down, for ground, and E for excited, acquires a global phase, and this global phase we can compute. So this is a global phase. But interestingly, in the full wave function, this global phase for different NJ sectors is a different phase for different magnetization sectors. So this is the steady state that you have for each NJ sector, but this corresponds to a phase for the different NJ sectors that we can try to correspond to the mean field phase here. But you can see that what happens is that this global phase that appear in my system appear as almost there. Applies as a phase that depends on SC in my S block vector. So the interesting part is that then if I let my system go down, back, then I do a closed trajectory, and I can see that I can associate a Berry phase in my J block sphere. And this Berry phase is the standard Berry phase that you have an spin moving in a closed trajectory that depends on the area in a circle. This area depends on cos theta, the angle, and you can compute that, and that's what we expect. We can nevertheless start to go from mean field picture to introduce quantum fluctuations, and we change the C numbers by operators. So NJ, you can change it by N half minus SC, and we can add hats to everything. And if we assume that the detuning is small, so the steady state behavior for a small detuning is still valid, when we plug this replacement into the mean field equation of motions, we see that in addition to the omega b sigma c that SC that I showed you before at the mean field, there is another term that is in the form of SC squared. So what happens is that if in the S wave is block sphere, when you do this Berry phase, you ended up with one-axis twisting dynamics having. So you start to have a spin squeezing. That is great. So this is that the Berry phase introduced to, because of the anticipative process, give you OIT dynamics. And well, I know that I'm running out of time, so I'm just going to say that this was the elastic part, because in the when you introduce a detuning, there is going to be some light in the cavity, because it's not cancelled out anymore. This light introduces some distinguishability in these different NJ sectors that introduce some type of dissipation. You are going to have not only a C square as a Hamiltonian, but you have an SC dissipative operator, and you're going to have a competition between the elastic interaction, that is the effective K, and the inelastic process. But the important part, and this is the main message, is that you can see that all of them become faster as you increase theta J, that means as you increase the population of the excited state. So this is a process where we are going to have a spin squeezing much faster, because you don't have to adiabatically eliminate the excited state. You can populate it and still get a squeezing in a fast rate. And moreover, if you turn off the drive, the spin squeezing is stored in the clock manifold. Moreover, the rate between these two, well, there is a competition, and therefore, as you go closer to the excited state, these terms start to win, so you have some decoherence. So just to finalize, because I know that I'm going out of time, this is the collective physics. You can have also some type of spin flips. This doesn't happen in the clock transition, but you can have spin flips, or you can have some type of dephasing in the system. And when you compute all these terms, you get the standard scaling of the entanglement that you can generate in the presence of dephasing. You get the n to the 2/3 scaling of the one-axis twisting. With the spin flips, you get more like a square root of n scaling, but overall you win in speed. And that's one of the big advantage. And in fact, we have computed what you can get for standard parameters, even with this type of flip-flop term that doesn't exist in strontium, with a very large single particle dissipation. You can get approximately 20 dB in our system. So strong symmetries in collective multi-level systems allow for the presentation of quantum information. The detuning of the drive dynamically generates spin squeezing very rapidly, and the squeezing is mapped in the clock transition. And with that, I think I'm running out of time. So I told you a story that we measure non-equilibrium phase transition. I told you that the strong symmetries can be useful for metrology. You can generalize it to more levels, and this is something that we would like to extend to the previous work. And moreover, Rosario Facio is not here, but we can even combine them with measurement at feedback, and we can generalize the phase transition that I discussed to this type of cases. And Rosario is going to give a talk on Friday about that. And with that, I think that there is a very highly excited physics ahead. And thank you for your attention.
Hi, Anna. Thanks for the talk. It's great. So I think one of the reasons people cared about strong symmetries in limited equations is because you can have passive error correction when you spontaneously break it. So maybe I lost, but do you have or do you see some options to create phase transitions in cavity QED that spontaneously break strong symmetries to start to think about passive error correction in that context?
Yes, I think so. I mean, I think you will, in this case, we will have 3-level systems. I mean, because the symmetry is the number of atoms in one of the sectors. And then we have this other, I mean, in this case, at the moment, we have been just, the other state is completely inert, nothing is happening. But I imagine that I start to have something that you have some dynamics in the system, that you are going to have some competition. I mean, maybe you have something that, I mean, you can have 2 different types of symmetry sectors that are coupled, and maybe you can see such type of phase transition. I mean, that's a good question. We have not explored it, but yes.
Okay, thanks.
So thank you, Anna. Very interesting. I have a question regarding the scaling with the number of particles. Mm-hmm. And I understand that the larger is the number of particles, the bigger will be the squeezing, the noise reduction, as well as the speed with which the entanglement is achieved. I understand, however, and correct me here, that the treatment is perturbative. So if you increase too much the number of particles, at some point the type of description you apply will break. So there is going to be an optimal...
Yes, that's an excellent question. And the point is that I didn't have time to explain, because we did generalize it. We have expressions for any regime, parameter regime. We use a Hofstede-Primakov transformation instead of this picture. It's more complicated, so I didn't present it here. But the results are the same. And we can optimize, I mean, all these expressions are actually optimized with respect to the full solution. These are not for a small detuning. These are generic solutions and we have solved numerically the full system. We can use this strong symmetry to increase the number of atoms. We have gone up to 1,000 atoms, and we see all these analytic predictions reflected.
I would like to, I tried to reformulate, okay, because maybe you answered, but I didn't understand.
Okay.
So when you introduced the model, you introduced the parameter chi and gamma.
Ah, okay.
And they are derived in the limit in which you can assume that the excitation is of the dipolar transition is negligible, right? But if you increase the number of particles, you start to go out of this regime. So I guess, yes, you are going to have to define on the basis of the saturation parameter what is the largest squeezing you can achieve and the fastest.
Yes. So this, what I'm saying is that this assumption you are saying here, right, is only pedagogically, because I wanted to provide a simple explanation here. We have been able to generalize this expression. They change the expression for chi are not, when I present them, they are not exactly that. They are much longer and more complicated. But still, so still, I mean, these are just the small delta limit because the expression fit here in the blackboard, in the talk. But all these expressions that we have here for the optimization, these are for the full solution. And yes, there is a compromise, and we can see that now you can see when you are going to have, because the dissipation, you see, becomes more important as you are closer to the equator. So this dissipation is worse. So in principle, you want to say, okay, in order to balance, I wanted to go to a small detuning. But for a small detuning, you are going to take longer time, and therefore, if you take longer time, you are going to be killed by these spontaneous emission rates. So actually the optimal value that we found for this parameter, this is the optimal value explored numerically on all possible parameters, and is that. So you have to optimize, and depending what is the value of the dissipation, you have, I mean, this is kind of the optimal. You can depends on the minimum of this expression, you can choose what is the optimal time and the parameters.
Thanks, Ana Maria, for the great talk. I have a question/comment on the use of the Davis-Cummings model. So we recently looked into this after long-lasting discussions of whether putting a finger into a cavity is correctly described by the Davis-Cummings model. And it turns out that no, because actually the Davis-Cummings model is only correctly describing the dynamics if the OD is small. Mm-hmm. So you actually have to compare the collective coupling strength to the free spectral range of the cavity. Mm-hmm. And now here, putting many strontium atoms into a cavity, is this condition fulfilled that the collective coupling strength is smaller than the free spectral range? And also, you have to look at the scattering rate into non-cavity modes. That also has to be much smaller than the free spectral range.
Yes, no, I think we are in this regime, but I think you are going to have to add more terms in the Davis-Cummings model. So I think you are going to change the coupling. You don't, I mean, I have seen when people write in microwaves that you have to add higher order terms in order to describe these extra terms. Like you have to add,
I think the problem comes from just having A and A dagger in your model, while having a high OD ensemble in a cavity makes it a multi-mode problem. So
okay, that's what you are talking about.
So you can actually, while in your model that you use here, there's just one mode, and you assume some kind of global response of the mode to the dynamics of the ensemble. One would more naturally separate it into, say, left of the ensemble, right propagating, right of the ensemble, right propagating, so having some kind of 4 modes in the cavity.
I see. Okay.
And it can the dynamics qualitatively is different. I mean, the spectrum is different.
Yes, we are not coupling to other modes. Maybe James can respond, but yes, the coupling to other modes at the moment is negligible. But I mean, I was thinking that you were saying you have to include terms that are non-linear in A. That sometimes needs to be but that's not. Mm-hmm.
No, not that.
Mm-hmm. The free spectral range of the cavity is so much larger than the sort of frequency scales you're talking about. That's still a really great approximation. With respect to what I'll call lensing effect, essentially you can couple from the TM00 mode into TM1010.
Yeah.
Right. But let's just think that the atoms are kind of like a lens that can sort of scatter into higher order transverse modes. It turns out that, like, if that ever became a problem, we don't think it is at this point. We don't see that. If it ever became a problem, you can imagine that you simply aperture your mirrors so that you make the higher order transverse modes lossy, and in some sense, you quantum Zeno effect that away. Right. So we have things right now. It's not an issue.
But the OD of the ensemble is small, because this is
yes, it's very true. I mean, we don't include any dipole.
It seems strange to me that the experiments are performed in the regime of small OD.
Our single particle C is about 1.
Yeah.
We're working with anywhere from 1,000 to 1 million atoms, but our finesse is also around 10 to the 5. So divide out by 10 to the 5 in order to get the sort of single particle resonant optical depth.
I mean, I would love to have more
discussions. We can discuss, and we, for example, we have even included at some point what is the effect of dipole-dipole interactions from the array, and they're negligible for the parameters. But yes, we should talk more.
One more question, Hugo. Sorry, I'll be quick. Very nice talk. I was wondering, how does entanglement survive the fact that you have now this single particle spontaneous emission when you go close to the transition?
Yes.
And yeah, I'll stop there because.
Yes, great. I mean, it's not that it survive. I mean, if you let the system evolve forever, that's the entanglement is going to be destroyed. So it's going to be an optimization between the time at which you are generating the squeezing and the time at which dissipation is acting. So we optimize the two. So, and that's why we cannot get, I mean, this cuts the amount of entanglement.
Sorry, I meant for the first part, for the first part of the talk.
For the first part of the talk, okay. I mean, this is not a spontaneous. In this case, well, I think Effie is going to give a talk about in the presence of single particle dissipation. But in the presence of single particle dissipation, there is entanglement not necessarily survives, but at very long times. It's going to be a transient effect. But I mean, he will have some comments on some type of jumps where you can actually select where you have not you can still have an spin intact squeeze state.
Yeah, okay, thank you.
Let's thank Ana Maria.